Hi, this is Nick Seifert, and welcome to lecture number 8 in the Advanced PowerPoint Design class at Carnegie Mellon. This is the spring 2014 semester. This lecture is on coal and waste gasification. We're going to be talking about how you turn carbon-based fuels into syngas. So this is going to be an overview because many of you may not be familiar with the concept of gasification. It's been around for a while, and I'll go later in this lecture into the history. For now, I'll just give a kind of a brief definition of what gasification is. Gasification is a process that turns carbon-based materials into what's called synthesis gas. These carbon-based fuels could be coal, biomass, wastes, plastics, any number of carbon-based products. And then that syngas is going to be comprised mainly of carbon monoxide and hydrogen. And that's what we're referring to as the syngas component of it. Of course, depending on what you put in, you may also get carbon dioxide, water vapor, and other smaller compositions of methane, ethane, hydrogen sulfide, and perhaps tars. The syngas, so the hydrogen and carbon monoxide component, can be used as a fuel either to generate electricity, can be combusted to generate steam, or it can be used as the building block for a number of chemicals. These chemicals, the hydrogen, if you convert it into hydrogen, you could use that hydrogen directly in fuel cells, or you could use the hydrogen when combined with nitrogen to make ammonia. The carbon monoxide and hydrogen, when combined, can make methane, ethane, ethylene, ethane. I was going to say which can be, or precursors to polyethylenes, like polymers. So the goal of gasification is to turn low or negative value feedstocks. So low value feedstocks are coals. Negative value feedstocks might be things like pet coke, petroleum, which is petroleum waste from petroleum refineries, or municipal solid waste, MSW. Those are negative value feedstocks, meaning you can get paid because normally someone would have to put them into a landfill, right? So you might get paid to turn these into carbon monoxide and hydrogen. So this is a very kind of simple breakdown. This is one example of a gasifier. It happens to be one of the gasifiers that's selling a lot recently, and it's a picture of an entrained flow gasifier. And I just want to point out here that the conditions can be quite extreme in these entrained flow gasifiers. We're talking pressures up to 70 atmospheres, and you can sometimes even see more. Temperatures up to 1400 degrees C, and the environment can be highly corrosive because of the molten slag, as well as gases such as hydrogen sulfide. I want to point out that these entrained flow gasifiers are some of the higher temperature and pressure gasifiers. There are many other types of gasifiers that operate at much lower temperatures and or pressures. I just want to point out, that some of the we'll call it some of the modern ones are operating at very high pressures and temperatures. And what you're doing inside the gasifier is you're mixing water and coal and likely slowly feeding the water and coal in. So you're taking low pressure water and coal, putting them together, and then slowly pumping them up to the pressure of the gasifier. You're also taking oxygen. That oxygen is probably coming from a cryogenic separation plant in which you cool air down and distill out oxygen from nitrogen. And at that point in time, when you distill out liquid oxygen, it's fairly easy to compress it then to the atmosphere, to the pressure that you need in your gasifier. Of course, you got to heat it back up, but that's not too hard because, as I said, the temperatures here are very high, and it's very easy to get the temperatures of the oxygen back up to where they need to be to enter the gasifier. So then the products that are coming out, we've got carbon monoxide, we've got hydrogen, and so the key thing here is that you're supplying enough oxygen to basically create a flame, enough energy to keep this thing oxidation going, but you're not providing enough oxygen to fully combust the coal. you want to be able to supply enough oxygen so that there's no carbon. So you need at least one oxygen for every carbon. Of course, some of those oxygens could be supplied from the water, providing you then with carbon monoxide and hydrogen, and that ratio can be adjusted by adjusting the amount of water that you put into the gasifier. Of course, because there's going to be likely there will be sulfur in your, and because there is sulfur in biomass, and biomass is is what coal eventually was a long time ago, and because there's often sulfur in a lot of municipal solid wastes, be that maybe if you were to put tires in here, there's often lots of sulfur. Even though there's a lot of carbon in tires, there's also a lot of sulfur. So depending on what your feedstock is, and I want to point out another one, pet coke, petroleum coke, some of the carbon buildup in petroleum refineries, that it's called pet coke, and that is often very high in sulfur, which is one of the reasons why it has to go to special type of landfills. But you could take it to the gasifier, but just be aware you're going to be making hydrogen sulfide or carbonyl sulfide, COS. And in this gasifier, you also, if it gets high enough temperature, the ash in whatever your feedstock, if your ash could be coming from the coal or from biomass or municipal solid waste, even pet coke is going to have some heavy, perhaps heavy metal ash content. These things are going to become molten and then are likely going to be molten on the side walls, perhaps interacting with your wall material. Just want to point out that it's one of the definite areas of research is the molten ash wall interaction. So before you can do anything, you're going to have to get rid of those byproducts that you don't want. Okay, but of course the drive here is that once you have the carbon, if you clean the carbon monoxide and hydrogen, you now have the building blocks for the three major industries. Right? You have the hydrogen that can be used in PEM fuel cell vehicles to drive your car, which, as you're saying, if you live in Los Angeles right now, you can purchase PEM vehicle fuel cells. The second one, electricity, is available almost everywhere, right? So you can combust the carbon monoxide and hydrogen and generate electricity, or you can use it as the building blocks for polymers or fertilizer. So here's a breakdown of some of the chemical reactions going on. So if we're taking coal, combining it with oxygen and water vapor, we could have carbon and half an oxygen going to carbon monoxide. We could have the full combustion creating carbon dioxide. We can have something called the boudoir reaction, which is when carbon and carbon dioxide form 2 carbon monoxide. We can have the steam coal gasification reaction, which is carbon and water vapor making carbon monoxide and hydrogen. We can have a methanation reaction in which carbon and 2 hydrogen form a methane molecule. We can have something called the water gas shift, and this could occur inside the gasifier, and it could also be occurring outside of your gasifier. Particularly if the goal of a water gas shift reactor outside our gasifier would be, let's say, if you wanted to tweak the H2 to CO ratio, you'd maybe add in water so that you had more hydrogen and less carbon monoxide. Or if your goal was to make hydrogen for PEM fuel cell vehicles, then you'd put in a lot of water vapor and be generating hydrogen in that water gas shift reaction. Or some gasifiers, for example, there's a gasifier in North Dakota that I'll be talking about later, has a downstream methanation step where you take carbon monoxide and 3 hydrogen to form methane and water vapor, and their goal was this is an operating plant in North Dakota, They take coal, turn it into syngas, and then they take the clean up the syngas, take it to a methanation reactor, generate methane, separate any remaining CO2 from the methane, sell the CO2 for enhanced oil recovery, and sell the methane as natural gas. So here's some gas compositions coming out of gasifiers. Typically, you're talking about hydrogen concentrations. This is on a mole basis, right? On a mole basis, we're talking about 25 to 30% hydrogen, 30 to 60% carbon monoxide, 5 to 15% carbon dioxide, and 2 to 30% water, and 0 to 5% methane. That methane is highly dependent on the temperature and pressure. We'll see towards the end how we estimate how much methane there would be in a gasifier as a function of pressure and temperature. Of course, depending on your sulfur concentrations, you could have up to 1% of hydrogen sulfide. Typically, the carbonyl sulfide concentration is about an order of magnitude less than the H2S. That depends, of course, on how much water is in the gasifier. And you can have varying amounts of nitrogen. The nitrogen comes from a number of various places. One, there's going to be nitrogen in biomass and coal, because nitrogen is a component of amino acids in our so it's a part of our biology. So there's nitrogen there. There's going to be nitrogen coming from the fact that the oxygen is not going to be 100% pure coming out of the air separation plant. So nitrogen could be introduced there. I do want to point out that you could operate the gasifier using air, not oxygen. You could hypothetically operate it. In that case, your nitrogen content would be extremely large. And there you'd have a lot of nitrogen, and all the numbers I've shown above would have to be reduced by the fact that there's a lot of nitrogen in there. But no matter what, you're not going to be sending in 100% pure oxygen, so there's going to be some amounts of argon and nitrogen still in the oxygen stream entering the gasifier. And so because of both the organic nitrogen and the inorganic nitrogen coming from the air, you also have species such as ammonia and HCN. And these are going to need to be removed before they can. Just like the H2S and the COS, these are species that are going to need to be removed before you go to downstream equipment. So the goal of this graph is to show you the sliding continuum between coal gasification and coal combustion. Right? There's one sharp line, which is an air stoichiometric ratio of 1, which shows up here as an MAF of 2.5. So on this graph, 2.5 corresponds to an air stoichiometric ratio of 1, which means complete conversion. And everything on the left of that means you are at an air stoichiometric ratio less than 1. And everything above that means you're on a molar air stoichiometric ratio greater than 1. So let's start off at the near zero air stoichiometric ratio. What you can see is at this point in time, there's still carbon. You're feeding in carbon to a gasifier and you're not supplying enough oxygen, and you're still going to get some carbon exiting. Now you may be generating some carbon monoxide and hydrogen and small amounts of methane and H2S. It's going to take a fair amount of oxygen to get rid of that carbon. And here on that graph, that shows up on a mass air ratio of 0.7. And here, all the carbon has been effectively all the carbon has been consumed. And now, as you start adding oxygen, you start oxidizing the hydrogen and the carbon monoxide. you can see, you'd probably, if you want to operate a gasifier, you probably want to be operating near the point in which the carbon has just been consumed, because any oxygen added in after that is just going to oxidizing your fuel that you could be using for other purposes. So there's going to be kind of like there's going to be an optimal amount of oxygen, but you also have to look into the fact that to keep the flame going, you may need more than that optimal amount. But when you get particle sizes of smaller and smaller, you can get closer and closer to that optimal amount. So what happens is as you add more and more oxygen, you eventually just reach the point where it's just hydrogen, where it's just water vapor and carbon dioxide. And you can see that the hydrogen sulfide remains hydrogen sulfide almost nearly to that full combustion point. And then if you continue to add oxygen, now this is just looking like a coal combustion unit in which you have oxygen left over in the stream of water vapor and carbon dioxide, as well as sulfur dioxide. So here are some of the, here's a compare and contrast between combustion and gasification. Right, so combustion is full oxidation, whereas gasification is only a partial oxidation. Right, so there's an excess oxygen in combustion, whereas gasification can be thought of as oxygen starved. The primary product of the combustion is heat, right? You're in the form of steam, whereas your primary product of the gasification is that syngas. And with that steam, you can use it to heat buildings. Most of the time, it's being used to generate electric power. With gasification, most gasification plants are not used to generate electricity. There are a large number of gasification plants in China that are being used for the production of hydrogen to make ammonia for fertilizers, as well as the production of plastics. So actually a large, and here in the United States we have a few gasification plants that are being used to generate electrical power, but there's also a couple that are being used to produce, or there's one being used to produce natural gas, as well as others that are being used for the production of like ammonia or other chemicals. So here I want to point out, of course, coal combustion is the dominant in the world as far as generation of power, whereas gasification is still fairly new as far as there are not that many coal gasification plants compared to the number of coal-fired, pulverized coal-fired power plants. The efficiencies of coal combustion depend greatly on the age of the power plant. A lot of the older ones might have been in the 20% efficiencies. Today's most efficient ultra supercritical power plants, coal combustion power plants, are sitting in the 37 to 39% efficiencies. Gasification power plants are sitting typically in the 39 to 42%. This is if you take the electricity and divide by the higher heating value of the higher heat, so that's an enthalpy of the coal. One thing to point out here is that the emissions from a coal combustion power plant are often much higher than a coal gasification power plant. And one reason for this is that in the coal gasification, you create a gas stream in which it is very simple to remove hydrogen sulfide or particulates, because there is not a large amount of nitrogen and because it's at a very, very, very high pressure. So you can capture these species while you're still at pressure and without a lot of dilutant nitrogen, which means that emissions, cleaning up gasification power plants are very, very clean as far as particulate emissions, NOx, and SOx. They still will be generating the same amount of carbon dioxide if you don't capture it. But one key thing here is that it is a lot easier to capture CO2 at a coal gasification plant than at a coal combustion plant, because the partial pressure of carbon dioxide in that syngas stream can be orders of magnitude higher than the partial pressure of CO2 in the flue gas stream of a coal combustion power plant. And that's because of a combination of what I said before, the lack of nitrogen to dilute the partial pressure, and the pressure of that syngas can be up around 50 atmospheres, whereas flue gas has dilute nitrogen and is at 1 atmosphere. Capital costs for these power plants depend greatly. These are some fairly old values of in dollars per kilowatt hours. These numbers have escalated over time, particularly were escalating in the 2008 time period when the cost of everything was getting more expensive. It's a little bit difficult to tell where those costs are for right now, especially for gasification, because these are only being built, like one or maybe one every couple, or here in the U.S., maybe one every a decade. In China, they're being built a lot more, I would say, I think on the order of one every couple of years. Okay, next I'm going to talk, show a little bit more pictures of what's going on here. Just trying to remind everyone that this gasification is an extremely flexible type of concept, because we can be taking in feeds such as asphalt, carbon-based feeds such as asphalt or coal or heavy oils. These are oils that are extremely high in viscosity. Petroleum coke, which is, as mentioned a little bit before, but it's this buildup often in catalyst beds, or particularly where they are trying to change the carbon to hydrogen ratio of the, they say they're trying to get rid of some of the carbon to make it a lighter oil. A lot of times you're left over with this coke. By coke I mean like graphite. It's a solid. Coke is like a graphite material with a lot of impurities such as sulfur, maybe some nickels, some of the catalyst might be in there as well. And then you have, you could potentially also take natural gas, mix it with oxygen to make syngas, and then that's something called gas to liquids, where you take natural gas, combine it with oxygen to make carbon monoxide and hydrogen, and then you turn that carbon monoxide and hydrogen into gasoline or diesel fuels. You could also take in waste materials such as municipal solid wastes into a gasifier. I previously worked for a company that did exactly that. The company has operating waste gasifiers in India, as well as Japan and China. And they take in Turkey, and they take waste and they turn it into carbon monoxide and hydrogen. So here, and then you have your gasifier, and you're going to be creating some ash out of your gasifier, and you're going to be taking it to the cleanup. One of the cleanup steps will be the removal of the whole hydrogen sulfide and carbonyl sulfide, and it actually can produce a marketable byproduct, which is sulfur, which would be used in fertilizers. And then you'd be taking that gas, that carbon monoxide and hydrogen, and either sending it to a combined cycle power plant, or you could be using it, as I said before, to make hydrogen, ammonia chemicals. And these chemicals could be such as methanol or precursors to plastics. Okay, this is the same slide, just from a different perspective. We got our feedstocks coming into the gasifier, ash coming out the bottom. This is showing, once again, all the different options we have available. So gasification, once again, is extremely flexible. What I said, you can separate out the hydrogen for transportation fuels. You could also take the hydrogen directly to a fuel cell to generate. Your fuel cell could be your electrical source at the power plant, rather than a combined cycle. But what we're seeing right now, as far as electricity generation, is the fuel going to combined cycle Brayton where it's a combined Brayton and then followed up by a Rankine cycle. And here's even more to follow up what I meant by gasification is extremely flexible as far as what we mean. There are a number of different types of gasifier types, and we'll be going through those in this set of slides. A number of different environmental control systems, as well as a number of different options for conversion or final products. Next thing I want to do is I'm going to compare and contrast a conventional coal power plant with a IGCC power plant and just give you a feel for the flow of enthalpy throughout the power plant. So in this case, we're going to start with there being 100 megawatts of enthalpy. This is the combustion enthalpy of the coal. So at a conventional pulverized coal power plant, you're adding in coal into a boiler, and so that 100 megawatts enters into the boiler, and then it's being used to heat up steam. Maybe about 85 megawatts of the original 100 megawatts goes into the steam, which means about 15 megawatts is leaving, enthalpy is leaving in the flue gas. So that 85 megawatts of enthalpy of steam goes to a steam turbine, and in the ultra supercritical power plants, modern coal power plants, about 40 megawatts of that 85 megawatts of steam can be exited as electricity, and the other 45 megawatts of electricity of enthalpy leaves as cooling water. Now, just as a reminder, I'm not talking here about exergy, because as a reminder, there's very little exergy in that 45 megawatts of cooling water, and there's very little exergy in that stack flue gas. Right? The amount of exergy is maybe 2 megawatts and 2 megawatts in the stack, and maybe 2 to 3 megawatts of exergy in that cooling water. But on an enthalpy basis, remember, doing a first law around this entire thing, we have an input of 100 megawatts, and then we have an output of 40 megawatts of electricity, 15 megawatts of flue gas, and 45 megawatts of enthalpy in the cooling water. Okay, so in that last case we had an efficiency about 40%. Coal-based IGCC power plants are typically around 40 to 43% as well, but it's going to look slightly different. So in this case, we're going to take that same 100 megawatts of enthalpy, and we're going to feed it into a coal gasifier. In addition, we're going to send in some oxygen. That oxygen is actually going to be needing 9 megawatts of electrical energy, which we're going to have to subtract off in our final calculation of the power. So that goes into the gasifier, as well as steam that was generated from the syngas when you cool it. And so then we have what's going to be entering into the Brayton cycle is going to be 80 megawatts of enthalpy in the form of hydrogen and carbon monoxide. So we're going to combust that in a gas turbine. We're going to generate about 30 megawatts of electricity, and that leaves us with about 50 megawatts of enthalpy in that flue gas. And from that flue gas, we're going to take it to a heat recovery steam generator. We're going to generate some steam, and we're going to have steam, that 15 megawatts of steam that was generated from the syngas cooler as you cool down the syngas. So that when you combine the 50 megawatts of thermal energy input plus the 15 megawatts of steam entering, that 65 megawatts gets converted into 18 megawatts of flue gas enthalpy leaving, and then a generation of 47 megawatts of steam, which go to a steam turbine. Of the 47 megawatts, 22 megawatts gets turned into electricity. The other 25 megawatts goes into cooling water. And of course, the net power was going to be the 30 megawatts generated in the gas turbine, plus the 22 megawatts in the steam turbine, minus the 9 megawatts of the oxygen plant, leaving you with a net efficiency around 43%. This can also be shown in what's called a Sankey diagram. This is a little bit closer to what we'll be discussing later when we show exergy, when we try to calculate the exergy destruction in each of the subsystems. Here, what's happening is you're flowing through the raw exergy of fuel, and you can see where exergy is actually lost and where exergy is taken and moved other places, such as that steam that heat bypasses steam coming from the gasifier from cooling the syngas and being sent over to the steam cycle. And here, this was a calculation done back in 1989, calculated about net efficiency of 40%. Efficiencies now are close for a coal gasification plant without CO2 capture are now closer to the 43%. The next thing I want to do is give a little bit of a history about fossil fuel use. Well, the history goes back to a very, very long time. In China was one of the first countries to start using coal, and then it really started taking off around in the 1800s. And in the 1800s, there were actually a lot of coal gasifiers. Actually, most cities had their own each town or city would have a coal gasifier. So it's kind of interesting that coal gasification, well, right now is not a concept very well known. It was a very, very well known concept over 100 years ago. And so towns would have these combined processes in which they would take coal, combine it with partially combine it with oxygen in one reactor, and then take those hot coals over to another reactor in which they would quench it with water. And the act of quenching it with water would cool it off, but it would also generate hydrogen and some carbon monoxide. So that gas from the quenching with the water would be then sent in pipes, and it was used, like if you've ever heard the term the gas lamp district in San Diego. These are gas lamps. Originally, gas lamps are coming from, the gas is coming from these coal gasifiers, where you're taking hot coal, mixing it with water, and that town gas is about 50% hydrogen, with the rest composed of methane, carbon dioxide, and between 3 to 6% carbon monoxide. It was very practical for street lighting. Unfortunately, people were also using it in their residences and businesses. And the problem, of course, is the hydrogen sulfide and the carbon monoxide. And it is very, very dangerous if you were to have a leak, because then you're basically breathing carbon monoxide and hydrogen sulfide. So this concept went away, particularly with the advent of drilling for natural gas. So you can talk all you want. We hear a lot about how natural gas is ruining the environment, but it was a major step up from town gas because people weren't dying from carbon monoxide, and people were at the time. People were dying from hydrogen sulfide and carbon monoxide poisoning. And modern natural gas industry produces a product that is safe for us to use in our homes. Safe for most of us to use in our homes. There's always going to be some people who will figure out how to misuse it. But so what I want to point out here is gasification really started taking off. It went out of, with the advent of natural gas drilling in the early 1900s. Those town gas plants started closing down, and there was almost no gasification, particularly around World War II. other than in a few places such as Germany, where there were just large amounts of coal reserves and not much of natural gas. And then what you started seeing was locations around the world where there were large coal reserves and and not as much natural gas. You started seeing in the 70s and then the 80s and 90s a generation of coal gasification plants. And one of the first big jumps in the late 1970s is shown here as the Sasol 2 and Sasol 3. These are coal gasifiers in South Africa, which were used to generate liquid fuels. This was they were taking coal and turning it into liquid fuels, and this was starting around the time in which there was a ban on selling liquid gasoline fuels to South Africa. So South Africa decided to create their own liquid fuels. There were also here in the U.S. A plant that was partially funded by the Department of Energy. It's called the Great Plains Synfuels Facility. It's in North Dakota. It is operating. It is paying back the Department of Energy as we speak, and it was the first commercial U.S. scale coal gasification plant, and it's taking coal and turning it into carbon dioxide and methane, selling the carbon dioxide to Canada for enhanced oil recovery, and then selling the natural gas into pipelines. One of the first coal gasification IGCC plants was demonstrated in the mid-1980s. It was called the Cool Water Plant in the U.S. We also have the Bungerman plant, which is in, I believe, the Netherlands. We have a DOE-funded the Wabash River and the Tampa Electric Pole in the 90s. And then we have another plant, the Puerto Leño plant in, I believe, Spain, coming in just before the 2000s. And then most recently, Duke Energy, a few years ago, just built an IGCC power plant in Indiana. So here I'm going to be going through a couple of slides and we talk about the different types of gasifiers. So the first thing we'll talk about is the gasification agent. We can be using pure oxygen coming from an oxygen separation plant, or you could potentially just use air. Now, you probably would not be using air if you are trying to make chemicals, or if you're going to do CO2 capture, because you have all this nitrogen diluting. But if you just were to do, let's say, biomass gasification and then do that for power plant production, you may potentially just use air because you don't want to do the oxygen separation. And that would be the case if you didn't need to capture CO2. You have a number of different flow geometries. You could run a counter current. This is where the coal may be dropping in from the top and your oxygen coming in from the bottom, and then they're running counter current to each other. Or you could have a co-flow in which your oxygen and your coal and steam all start in the same location and end in, and then your syngas is all coming out, let's say, the other side of the reactor. You could have variable feed size. You could have small, meaning only micron size. Or we could have anything up to coarse, which means if you put in municipal solid waste and you're putting in something the size of a plastic cup, right? Here we're talking about a macroscopic scale. And then ash removal can be done. The ash, depending on the temperature gasifier, you may stay below the ash melting point, which we call that dry ash removal, or the ash may leave as a slag, and we could call that wet ash removal. And that's when the temperature at which when the slag is leaving the gasifier is above its melting point. And that melting point is a function of a lot of things. Largely it's a function of the ratio of the number of basic species to acidic species in ash. And what I mean by a basic species we're not talking about aqueous bases. We're talking about solid bases or solid acids. Solid bases are lime, or calcium or magnesium oxide, or other basic species are potassium and sodium, or if you happen to have lithium. These are all bases, solid bases. The solid acids are silica, SiO2, or alumina. And then, something that would have a very, very low melting temperature is typically when the base to acid ratio is close to 1. And so when you have like equal amounts of the acid and base, that typically creates a low slag melting temperature. And as you move away from that ratio of 1 to 1, that's typically going to cause a higher slag temperature. So something like lime, if you just have a lot of lime, it's going to take a very, very, very high temperature to melt lime, or a very, very high temperature to melt just silica. But when you were to mix silica with lime, and particularly if you were to add in some sodium, that's when you can start getting the temperature of your slag to start dropping down. So whether or not you have dry or wet ash removal depends on the ash composition as well as the temperature. Okay, so here we're going to be, this is the word description of what I'm going to be showing in pictures. We have the gasifier types. We've got a moving bed, and Lurgi is the most famous of the moving bed gasifiers. We have entrained flow, and this is GE and Shell and ConocoPhillips as well as Siemens. Train flow gasifiers are slagging gasifiers. They're run at such high temperatures that you're going to be above the melting point of the ash. And then you have the kind of in between these two is the fluidized bed, and this could be either a transport gasifier or a high temperature Winkler gasifier. So I'll be going through all in the next couple slides. Okay, so let's start off with the example of the moving bed. And I'm going to show it here, but we're also going to spend some more time in detail. So the moving bed is a counterflow gasifier. So we have coal coming in the top, and on the bottom is the steam and the oxygen. So what's happening here is there's a lot of things that are happening, but one thing we can say that is happening is it's also is very much like a counterflow heat exchanger. So if you look at this diagram of the temperature as a function of the top to bottom of the gasifier, that coal entering from the top is being heated with the gas that's leaving. That's very much like a counterflow heat exchanger here. The coal is being heated up and the gas is being cooled off. So the gas can leave here at maybe around 1,000 degrees F, which may be on the order of 500 to 600 degrees C. And once again, we have a counterflow heat exchanger on the bottom. What's happening is that the oxygen and steam are coming in cold, and they're being heated up by the ash that's leaving the system. So the ash is going to be acting like the hot side of a heat exchanger, but there's no wall material. It's just direct heat exchange, and this is in some sense a very, very efficient type of gasifier because it's built in a counterflow mode. Just as we said before, counterflow heat exchangers are typically a lot more efficient than co-flow. A moving bed is a very efficient type of a gasifier as far as the efficiency goes. And then what I want to point out is in the middle of the gasifier, the oxygen is going to start reacting with any carbon left over. So what happens if we can follow the track? What we'll do is we'll follow the track of the coal. The coal comes in, starts getting heated up. The first thing that happens is that any water vapor in the coal starts evaporating, and then that water vapor will just leave. The next thing that happens is the coal may start what's called pyrolyzing. Methane, ethane, tars, carbon dioxide, hydrogen, parts of the coal just start breaking apart. It's called pyrolysis. And it starts breaking apart, and some of these species will leave the gasifier. And in this moving bed, as I said, one of the products that comes off pyrolysis can be tars, meaning highly viscous, high molecular weight hydrocarbon or hydrocarbon oxygen species. It can pyrolyze, meaning vaporize off of the coal, and then you can see if it happens to the top, it's very close to the exit, so that can be leaving your gasifier. So some of these products these moving bed gasifiers produce the most amount of methane and tars. And that's because when they pyrolyze, they're so close to the exit. So the next thing that happens is the coal will be running into steam and carbon dioxide, and you'll be generating then some carbon monoxide and hydrogen. And as you start moving towards the bottom of this bed, and the reason it's called a moving bed is that the material just slowly moves through this bed material. So you could track a piece of coal, and it would start at the top and then slowly move through the bottom. And by the time it got towards the bottom, what would be left is mostly just graphite, the hardest. So you have a lot of pyrolysis products coming off, and then some of the carbon will be interacting with the water vapor, but what's left is very much like graphite, and it's hard for steam coal gasification to attack that graphite. So that's part of the reason you need oxygen in this gasifier, is oxygen will react with that graphite fairly quickly. So that oxygen is reacting with the What's nice, the other reason this is a very efficient gasifier is the oxygen is not reacting with the methane that pyrolyzes off. There's no oxygen by then. The oxygen is going after that hardest to combust or oxidize carbon, that graphite form. So it's a very efficient use of the oxygen in this gasifier. It's attacking the graphite. It's not attacking the tars or the methane. So if you're trying to actually produce tars and methane, this is a fairly efficient gasifier. And this, for this reason, the natural gas power plant in North Dakota, the coal gasification plant that's making natural gas, decided to use a moving bed gasifier. Okay, let's go down then below that. Let's look at the fluidized bed. The fluidized bed, particle size of the coal has been reduced in size, and now the flow rate of the steam and oxygen is enough to create mixing a bubbly fluidized bed. And so it means what we've done in between moving from a moving bed to a fluidized bed is we've reduced the size of the coal. And what happens is transport increases when we do that. The gasification, all the rates start increasing because our particle size is smaller, which means it is easier for the oxygen to get into the middle of the particle and combust particles or oxidize particles to create the carbon monoxide and hydrogen. So reaction rates are going up. So one advantage of going the fluidized bed is the reaction rates can start going up. Now, you do lose some of the efficiency of the moving bed. You can see one thing here, that coal is not very. It's a very rapid increase in the coal temperature, which means the gas still leaves at a fairly high temperature. We weren't able to really cool the gas off when it left, and it was more difficult for the ash to transfer its energy to the oxygen that comes in. But in that middle region, we have extremely high fluidization and turbulent transport, which means the reaction rates are very fast in this middle section compared to a moving bed gasifier. But fluidized beds are a lot more difficult to operate because you have to have the right, as you can imagine, it's a very turbulent flow, and it's hard to predict A lot of research goes on nowadays on trying to how to model fluidized beds. So there's some advantages and disadvantages, and we'll talk a little bit more about that later. The next type of gasifier I want to talk about is up on the upper right is the entrained flow, and here we have co-flow. So the fluidized bed and the moving bed were counterflow. This one we have a co-flow. We're adding in coal and oxygen, coal, steam, and oxygen at the top, and the particle size now is so small that we can actually entrain the particles in the flow. And we're going to feed it all at the top, or sometimes you could feed it at the bottom and then the gas comes out the top. You have a lot of different options. But you entrain the flow, the particles in the flow, and in that case, because it's co-flow, what's heating up the coal and the steam is the act of combustion itself, and the particle size now is so small that these reaction rates can occur nearly instantaneous. And so the size for a given, the advantage of the entrained flow is the reaction rates are extremely high, which means you can decrease the size of your reactor. Reactions are taking place on the order of seconds. Compared to the moving bed, it could be half hour, right? So your size is greatly reduced, but your efficiency starts dropping. The entrained flow is not very efficient. There's no counterflow exchange going on. Coal and gas come in cold and leave hot, which is not very efficient. But if you can decrease your capital costs, you may have a case, right? The question, of course, always is the economics. So the question is, how do you find that optimal between low cost? There's the optimization between low cost and low and high efficiency. So finally, I want to point out there is such thing as a transport reactor, which is similar to a fluidized bed, but you may have multiple chambers in which you're creating and separating out the solid species and perhaps feeding that back into the main reactor. And it's very much like a fluidized bed, but now multiple fluidized beds. Okay, here's some more pictures of the gasifier types. Going through with starting on the left, this is a picture of the Lurgi dry ash gasifier, and in this case you're feeding in a solid, and so the solid starts off at atmospheric pressure, and you need to get that to the pressure. You can't just send in atmospheric feed. So in the Lurgi gasifier, this moving bed gasifier, they put in the feed, and they have this lock hopper system, and it's these. You have these two grates where that will open and close on time, and so let's say if you're trying to feed this system, the bottom it's this like moving wall. So the bottom one is closed and the top one is open. The feedstock will go in at atmospheric pressure. You then close the top feed, so both are closed. You then pressurize it with pressurized gas from your gasifier. You then are going to open the bottom one, let the feedstock drop in, and then you're going to close that, suck the pressure out of it so it goes back to atmospheric or below atmospheric, because you now have all this syngas that you don't want to release to the environment. So you have to empty out all the gas, and then you can finally open the top and put feed back in. It's not the most efficient, but it works, and lock hoppers have their own issues. It'd be nice if you could slurry feed it in, but when you slurry feed, you end up having to slurry it with something, and if that something is water, you may need a lot more water than your gasifier could handle. You'd ideally want to maybe slurry. If you had a waste material that was liquid, it would make feeding this gasifier really, really simple. Or if you could slurry your solids with a liquid feed, that would be very ideal. So this is the gasifier, and then it's a moving bed, and down at the bottom is this thing called the ash grate, and this thing is rotating, and it's pulling the ash out, and then you drop it down. There's an input down at the bottom for the steam and oxygen, and then finally you have an ash lock, and then you need to do the same thing you did at the top, right? Because that ash has got to come out at atmospheric pressure, but it's entering the ash lock at whatever the pressure of the gasifier is. So you need another kind of lock hopper system at the bottom. Okay, next to that is the British Lurgy. It's a slagging gasifier. It's almost exactly the same, except for this time the slag is kept above its melting point, which means it's going to leave as a liquid. So you don't need that ash grate, which means that's one less mechanical piece that could fail and then cause you to have to shut down your gasifier. But you're likely going to still need some ash lock hoppers at the bottom, because it's eventually going to get quenched and cooled and become a solid again. Next to that, we have a fluidized bed. It's like a transport gasifier. You can see here, in order to fluidize the particles, in this medium-sized particle range, you need very, very high velocities. So fluidized beds often look very, very tall and slender. That's often a sign that you're working with a fluidized bed. Moving beds do not need to look small and slender, because you're not trying to entrain or fluidize the particles. Okay, and then on the right, I have a couple examples of entrained flow gasifiers. And here it's extremely small particle sizes, and your gasifier may be lined with steam. And the reason you'd be lining it with steam is that you need to cool off the syngas, because if not, you'd be leaving at a really, really high temperature, much higher than any of your downstream equipment, your downstream cooling gas cleanup equipment would handle. So these gasifiers are more, it's a partial combustion in which because it's a co-flow, that energy needs to leave the system in the form of steam. And that's not always, in the counterflow cases, they're designed to be a lot more efficient and don't need to be steam cooled. So here are some more characteristics, just to give a comparison between these types of gasifiers. So in the moving bed one, we're talking about a feed size of about 1/4 of an inch to 2 inches. It's not going to be able to handle small fines very well, because they're likely just not to have the time to react, and maybe could just get blown right out. Most moving beds are done with a low coal rank. By what I mean, a low coal rank is a subbituminous or a lignite coal, which has much higher reactivity than a bituminous or an anthracite coal. And because reaction rates are fairly slow in the moving bed because of the size of the particles, moving beds are best for highly reactive coals. And those are the coals that have been under the ground the least amount of time, which are the lignites and subbituminous. The longer it's in the ground, the more it becomes like graphite, and graphite reactions are much, much slower than the reaction rates for a lignite coal or a biomass. So this is why for biomass you could be sending it to a moving bed. Municipal solid waste, likely municipal solid waste has typically the same reaction rates as biomass, or faster than biomass, and so a moving bed may make a lot of sense for a waste gasifier, particularly because it may be hard your municipal solid waste may be very hard to make into very fine particles. You may just, because of all the other junk that might be in the municipal solid waste, you may not want to pulverize it, so a moving bed makes a lot of sense for municipal solid waste. The gas outlet may be between 400 to 500 C. As I said before, it's a very efficient, and one of the signs of the high efficiency is the low amount of oxygen that's required. And one distinguishing characteristic I've already mentioned is that you will get a lot of tars and oils in the raw gas stream, which need to be removed in most of your downstream equipment. Now those tars, you may be actually trying to generate those tars. So I just want to point out, tars may or may not, it sounds like a bad term, but those tars actually might help you slurry feed in some of the coal. So there's potentially good or bad, there's potential benefit in having tars in your syngas. But it definitely means you have to design your downstream equipment to be able to condense out those tars. And then another characteristic of these moving beds is it's typically a very long residence time of the order of 15 minutes to half an hour. And that's the residence time. If you put a piece of coal in the top and you look at it, and as it travels down, and then you look at that ash, the ash that was part of that coal, and you look at how long it took for the coal to come in the top compared to the ash to leave out the bottom, that number is on the order of 15 to 30 minutes. And that's the same for a dry ash or a slagging bed. One thing I want to point out with the slagging bed, as I said before, the slag leaves molten because sometimes you'll add in something to get that base to acid ratio around 1 so that the melting point is fairly low. And the next one, the entrained flow. Here what we're talking about, when I mean pulverized, I mean less than a quarter of a millimeter, which is 250 microns. So we're talking about extremely small size. And here it needs fines. You can't be sending in large pieces of coal. And almost any type of coal is fine as long as you can put it into that pulverized form. The gas is going to, before you quench it, the gas is very, very high. Temperature maybe around 1200 or more degrees Celsius. But because it was a co-flow and very inefficient, it needs a large amount of oxygen. And because it also needs a large amount of oxygen, it's going to be generating a lot of heat. So you're going to need cooling, and that either means quenching, which of course is extremely inefficient because you're basically doing co-flow heat exchanger but with no wall material in between 1200 degrees C gas and 100 degrees C or so water, and letting the two equilibrate. And as you can imagine, that's extremely inefficient. But it can take place very rapidly. So once again, it's these trade-offs between efficiency and size. Because here, this fuel residence time in the reactor may be 1 to 10 seconds, right? That's a huge difference. If your gasifier can be 1/60th the size, well, if it's inefficient, you may still choose it if it's 60 times smaller. So I just want to point out there's of course always trade-offs. So, and then next things I want to talk about is fluidized bed. You could have dry ash or agglomerating. By agglomerating, I mean the ash may be melting because of its ash melting temperature. And here, pulverized, we're talking about it's the size of the particles in between the coarse and the pulverized. So that's between about a quarter of a millimeter to a quarter of an inch. So the next things I want to point out, the temperatures here, depending on how you run your fluidized bed, the gas could leave between 700 and 1200 degrees C. And this is really, the fluidized bed is the intermediate case. It's going to be consuming a moderate amount of oxygen, more than the moving bed, but less than the entrained flow bed. It is a counterflow, and that's one of the things that makes it fairly efficient. But the residence times just aren't as long at the top or bottom, which means there isn't as much time for that heat exchange to go on at the top or bottom. And I'd say one of the largest key issues with fluidized beds is just being able to predict the stability of the fluidized bed as you go from the pilot plant scale to the commercial scale. And that is one of major research areas, is can you actually take the data from a lab scale fluidized bed and design your pilot plant scale, and can you actually then take the data from the pilot plant scale and design your commercial scale plant? And it's very difficult because of the unique qualities. A lot of things are going on in the fluidized bed. And here I want to point out the residence time is about intermediate between the entrained flow and moving bed. We're talking on the order of 5 seconds to a minute. So there's going to be a lot of things that could affect a gasifier. That'd be the energy content of your fuel, the moisture content of the fuel, the amount of volatile matter. That's particularly going to be an issue in those moving bed ones. You may have a lot of tar production, and you may or may not want the tar being produced. Of course, the ash is going to have a major effect. If you just have a lot of ash, then you just are heating up and cooling a lot of ash, and that's very inefficient. And that normally ends up lowering the efficiency of your process. The reactivity of the coal is going to be important. Its size or size distribution, its density could be important. Particularly also its the graphite part, its char properties. Okay, now I'm going to focus a little bit more on that moving bed. This is kind of a zoom in, and we talked about how this is the extremely efficient because it's a counterflow design. And this is just a zoom in to see, show you more of what's going on. Right, as I said before, we have counterflow heat exchanger between the gas and the coal, as well as counterflow heat exchanger between the ash and the steam or oxygen. And then, so this is where the moving grate would be kind of at the bottom of this bed, and the coal is being dumped in at the top, and we have residence times on the order of 15 minutes to 30 minutes. The dry bottom Lurgi gasifier was developed with cooperation of the University of Berlin. It's now owned by Sasol, which is a South African company, and they are still designing new gasifiers. I think they're on the Lurgi Mark 5 or 5 Plus. They continue to make new gasifiers of this moving bed type. And as I said before, there's lock hopper feeders both in the entrance for the feed and then the ash as it leaves. There's that rotating grate, and because of the tar production, there's normally a quench afterwards, and then your clean gas free of tars would be then going into downstream equipment. Here's another zoom in of the Lurgi gasifier, and just showing the same thing. This time I wanted to point out this one, and this shows, this image on the right shows the breakdown where we have what I said before, drying, so the water vapor leaves, and then devolatilization, that's where the pyrolyzation is occurring. Methane and tars may be leaving. Reduction is when we start having steam-coal interactions, and then combustion is coal with oxygen. And then by the end you have no carbon or hydrogen left, and you just have your inorganic ash that is being used to heat up the oxygen and steam. Here's what a Lurgi Mark IV gasifier looks like. There's a picture of a person in this photograph. This is a photograph from the the Dakota Synfuels plant. This is in North Dakota. And at that site there are 23 Mark IV gasifiers, and these 23 Mark IV gasifiers are handling about 1/4 of a ton per second of lignite North Dakota fuel. and also handle about 57 kilograms per second of pure oxygen and about 300 kilograms per second of steam. Right, so these are very, very large gasifiers. And then the output, you've got 21 kilograms per second of ash, 13.5 kilograms per second of tars and oils, and then the bulk is about 600 kilograms per second of syngas. And that syngas is about 2% hydrogen, 10% carbon monoxide, 35% carbon dioxide, 4% methane, and then 1% of ethane or propane, and then 1% other gases, and some of that could be hydrogen sulfide, and then almost 50% water vapor. I do want to point out here, this was on a mass basis, that the syngas composition. If you were to do it on a mole basis, the one number that would greatly increase would be that hydrogen because of the low weight. But I do want to point out that this number was done on a mass basis. And so here's a picture of the entire facility, which is in North Dakota, and started up in 1984. It was part of a DOE loan guarantee at the time, and that loan is being paid off right now. How much gets paid off is often a large function of the price of natural gas. So, like when that number is really high, the amount of the loan gets paid back goes up, and when that number goes down, I think typically that amount that gets paid back goes down. One unique thing that's been happening recently is the CO2 is actually being captured and piped 205 miles away in Saskatchewan, and it's used for enhanced oil recovery. Here's another aerial photo of the facility. So now we're going to talk about the pros and the cons. So a lot of these have already been mentioned, but just as a re-emphasis here. Relatively low oxygen is required because it is a counterflow, high efficiency design. You don't need expensive heat recovery equipment because inside the gasifier itself, because of that counterflow design, you're cooling off the ash and you're cooling off the syngas as it leaves, and you're cooling it off with species such as the coal that need to get heated up, or the oxygen and steam that need to get heated up. So it's a very efficient type of process. It's suitable for coals or even, as I said before, municipal solid wastes. And it can handle municipal solid waste that may be very bulky and unable to be used in other gasifiers. And if your goal is to generate methane, well, it helps if your gasifier actually starts by making methane. Less yet downstream methanation you need to do. So this is potentially one advantage of this type of gasifier. The cons: it's not going to be able to handle coal fines. Caking coals, these are coals that will often, kind of in the way, caking is not the best term for it, but it's almost like popcorn. Some coals will just pop and expand in volume, and or form together with other coals and form this like bridge material that when the coals just start forming like large bulk coking products. So some of the particles will combine with other coal particles. If that is happening, that can be very disastrous in this gasifier, because it could cause what's called a bridge, where you have a solid species that spans the entire gasifier, and then you just are putting material on top of this bridge, and there's now a gap. The material below will start falling out because of the ash grate. But if you, it is something to watch out for in this type of gasifier, and it can be. There are multiple ways of getting around this. The gasifier I've worked with got around this problem by actually dropping a weight to break up bridges if they ever formed. But it's it's dropping on a weight to break this bridge. There are ways of getting around it, but you want to pick materials that are likely not to cause these bridge or caking and building together of the coal particles. And the last thing, the con. I put it here as a con, though it could be a con or a pro. There is likely going to be a large amount of tars being produced. Not large compared to the amount of syngas being produced, but large compared to entrained flow gasifiers, where in those entrained flow gasifiers, the coal is immediately contacted with oxygen, and those tars will immediately be oxidized. Okay, so that leads right into the entrained flow gasifier, which, as I said before, the coal and oxygen and steam are immediately contacting each other, and what's heating up the coal is the combustion process itself. It's not very efficient. As we talked in the case with the pulverized coal power plant, you don't want to just feed in oxidant and coal and watch and it combust it, because it's very inefficient to have a flame heat cold gas. And that's kind of what's happening here. Is there's absolutely huge temperature gradients, which means the potential for high amount of heat flow, and that's largely a source of exergy destruction. And then you have the gas and slag hot. You can't cool off the gas with the slag, or vice, as we were seeing in the counterflow cases. So you have to put in some kind of downstream coolant, quench or radiant cooler to cool this off, to cool off the syngas and the slag. So here are the main two different ways of dealing with that hot slag and syngas. First one here is called a radiant cooler. The second is the direct quench. So in the radiant cooler, what you're doing is you're putting in, kind of like in the pulverized coal power plant, you're putting in these pipes that are carrying steam, or they're carrying water, and you may boil the water to create steam, and that's going to be used to cool off the syngas. In the second one, you're just directly having the syngas go into a liquid bath, and that will quench the gas, quench the ash, and then the ash will drop to the bottom, and the gas will go up through the sides, bubble through the water, and then you have a gas stream that is saturated with water. So it will leave at whatever temperature it leaves and be saturated, i.e. 100% relative humidity. And so the entrained flow gasifier, very, very fast, means you can do all this in a very small size, but it is not very efficient. Here's a picture from the Tampa Electric Company, the gasifier in Tampa, Florida. We have the gasifier and the radiant syngas cooler, and then there's some other heat exchange convective coolers shown at the bottom. Just to give you a size, I don't see any people in this picture, but you can get a size from the dimension of the stairwells. This is absolutely large, multi-story tall. So here, the radiant boiler one. The pressure is going to be depending on your application, whether or not you're doing IGCC or for generating chemicals. And this type of radiant boiler was used in the cool water and the Polk gasification power plants. Here we're cooling off the syngas and generating steam. Whereas in that direct quench, as I said before, we're actually going through a bath of water, and this one is extremely inefficient. So this entrained flow direct quench is going to be the least efficient of all gasification designs, but it'll be extremely compact and simple in design. So of course there's always trade-offs, right? It's a very, very low efficiency, but can be extremely compact, and this has been used because of how gasification is not cheap. So anything you can do to keep the cost down is good, as long as it's not at too much of an extent cost of the efficiency. And so the temperature that saturated syngas is leaving is typically on the order of between 200 and 300 degrees C. The next thing I want to talk about is syngas cleanup. And just as a reminder, we have our fuel constituents, and that fuel constituents could be tars, or you may want to put the tars in the contaminants list, depending on if you see the tars as contaminants. You got non-fuel fuel species. This would be some of the dilutants in there, like carbon dioxide, water vapor, nitrogen, argon. And then we have our contaminants that we're going to need to get rid of. Definitely going to be needing to get rid of particulates, sulfur species, nitrogen that gets bound into the fuel in either the form of ammonia or hydrogen cyanide. We'll have the halides, right? The chlorines, bromines, fluorine, and that could be in coal. Could be if the halides are in the form of salts like sodium chloride, then they don't necessarily pose that much of a problem. Though of course, as the ash, we don't want the ash agglomerating on pipes or anything like that, or else that could cause pressure drops. But it is if the halides are in the forms of acid gases, then this is potentially a problem in either catalyst beds or just for steel pipe. Another contaminant is going to be mercury. Mercury is generally fairly difficult to remove, it's difficult to remove from high temperature gas streams. So if there's mercury in your fuel and it's going to be in the gasifier, it's going to likely be as gaseous HGO, meaning it's not oxidized, meaning it's the reduced form of mercury, but it's in the gaseous phase, and it's likely not going to drop out or condense as a liquid until you get to a fairly low temperature. There are companies that design sorbents that can capture mercury, and these sorbents are typically the lowest temperatures would be on the 100 to 200, meaning you're not going to be capturing mercury at like 500 degrees C. Whereas there are sorbents that will capture sulfur in high temperatures such as 500 or 600 degrees C. And then you're going to have other volatile metals, some of which may be difficult to remove, like arsenic and selenium. Others and maybe in the ash, such as calcium and potassium. And I do want to point out that when that iron and nickel have the capability of forming these carbonyls, which is carbon monoxide bonded with either iron or nickel, and this is something to watch out for. And they can form between roughly 400 and 900 degrees F. Next thing I want to do is we're going to move on to the thermodynamics, so we can learn how we'd model an equilibrium-based coal gasifier. Not all coal gasifiers are actually in thermal equilibrium, but we're going to, at least in this lecture, I'm going to show how you would model a gasifier if it were in chemical equilibrium. So one way of showing the range in which a gasifier operates is to make a triangle and in which we vary the amount of oxygen, carbon, or steam. And here we'd have a case in which you have an air stoichiometric ratio of 1. You could have the case in which you're just saying in carbon and oxygen, and then there's a minimum amount of oxygen that you need to supply, or else you still have some carbon left in the fuel. And in between these two lines is the range of a gasifier. When you go below the bottom line, you're now fully combusted, or when you go above the line F, you are into like a pyrolysis phase in which you haven't fully gasified the fuel. Some of it's still there's solids being left over. And here D is the other extreme, in which you'd be sending in just enough steam to turn the carbon into carbon monoxide and hydrogen. And so kind of the range above, so between C, F, and D is the range that's called excess carbon. We've got the range called excess oxygen, which is A, E, and B. And then in between, so between F, D, E, B, is the range in which gasification can occur. Okay. So one thing to point out here is that when we're solving equations in the gasifier, we're going to be setting constraints that the amount of carbon is equal to 0 and the amount of oxygen is equal to 0. So the reactions are going, there's 4 reactions taking place: carbon and half of an oxygen, carbon plus a full oxygen, carbon plus hydrogen, and then we have oxidation of water vapor. So these are 4 independent reactions. Now we're going to be able to eliminate one of these reactions because we're constraining that there's exactly 0 oxygen. So 4 equations is going to go down to 3. And these 3 equations can be written as, the first one is the Boudreau reaction, the second is a type of methanation reaction, and then the third one is the steam-coal gasification reaction. So what I did to go between the 4 reactions and the 3 reactions is we eliminate oxygen, right? If you notice, there's no oxygen now showing up in this set of 3. That's not to say that there aren't reactions that involve oxygen, but what we're saying here is that we constrain the oxygen composition, leaving the gasifier to be 0. So there is oxygen is not one of the products leaving the gasifier. So kind of what the way to think about this is that first reaction, either the first or second reactions take place instantaneously so that all the oxygen is consumed, and then you eliminate oxygen as a species, so you no longer need to use an equation that has oxygen in it, and you can go from these 4 equations into these 3 equations. The next thing we're going to do is we're going to also simultaneously constrain that the carbon leaving the gasifier is equal to 0. So when you do that, you only need 2 equations to model what is the output gas composition from the gasifier. And there are now 2 independent reactions. And what I mean by that, there's a lot of different ways of writing what those 2 independent reactions are, but the number can only be 2. Meaning, if you could write, so let me go through what those 2 are. So the first one is called I'm writing 2 of them though, as we'll see. You could do the first equation plus the second one, and then you get a third one. But that third equation would no longer now be independent. So I could either, if you add the first and second equation, you get a third one. I could either use the first and the third, or the second and the third, or the first and second, but I can't use all 3 because they're not now independent equations. So the first one that I wrote down was called the water-gas shift reaction, in which carbon monoxide and water vapor go to carbon dioxide and hydrogen. And then the second one is a methanation reaction, in which carbon monoxide and hydrogen are forming carbon dioxide and methane. So the key thing here is that we can write 2 equations. So this basically is going to give us 2 constraints. And as we get to the next slide, what we're going to want to do in order to solve for the gas composition is we're going to need the number of constraints to be equal to the number of free variables. So these two equations that are shown at the bottom are going to be two of the constraint equations that are going to be used to solve for the gas composition leaving the gasifier. And so these two equations, they are what I call K is equal to Q equations. And they are equations that relate the gas composition to equilibrium constants. So the equilibrium constants are K, and so K, the equilibrium constant, is a function of temperature only. For any given reaction, once you know what the reaction is, K is only a function of temperature. And K, what it actually is related to the Gibbs free energy of the reaction under standard temperature. Under standard pressure. But it's a function of temperature, so it's related to the Gibbs free energy of a reaction at standard pressure, and that standard pressure is where all gas species are at 1 atmosphere. And so what we see here is K is going to be equal to Q, and Q is what I call the quotient, or it's basically a fraction that relates the gas composition of the products and the reactants. So let's start off with the simpler of the two, the water gas shift reaction, which is on the bottom right here. So what we're saying here is that the equilibrium constant of the water gas shift reaction, which is a function of temperature, so all the temperature dependence is on the left-hand side. On the right-hand side, we're going to do our quotient, which is going to be, in this case, the composition, or it's going to be the partial pressure of the reactants, summation, the multiplicative summation of the partial pressure of the products over the multiplicative partial pressure of the reactants. It just happens for the water gas shift reaction, because there's an equal number of products on each side, we can cancel out pressures, and we're left with, we can pull up, instead of using a partial pressure of CO2, we can turn partial pressure of CO2 into total pressure times chi, which is chi CO2, which is the mole fraction of CO2. So what we have here is chi CO2 times chi of hydrogen divided by chi of CO times the chi of water vapor. And this equation was nice and easy to write, because for the water gas shift reaction, there's an equal number of gas species on each side. The methanation reaction is a little bit more complicated, because there's a change in the number of gas species. So this time, if we do the correct form of the equation using partial pressures, would be the equilibrium constant for the methanation reaction, K sub m, which is a function of temperature, is equal to the partial pressure of CO2 times the partial pressure of hydrogen to the 4th power divided by the partial pressure of methane divided by the partial pressure of water vapor squared. In this case, in the numerator, we can pull out p to the 5th, and the denominator we can pull out p to the 3rd. So what that leaves us with is that K sub m, as a function of temperature, is equal to chi sub CO2 times chi of hydrogen to the 4th times total pressure squared divided by the mole fraction of methane divided by the mole fraction of water vapor squared. So these are the two equations that we're left with. So what I want to point out here is we're going to now set up our solutions so that we have the number of constraints is equal to the number of free variables. So what I want to point out is here, for this, I'm using Y instead of chi, just because I grabbed from different slides. And but here Y and chi are the same thing. They're mole fractions. So what I want to point out here is that there are a total of 6 equations, and there's going to be 6 unknowns. So let's go through first what the 6 unknowns are. There are going to be 5 mole fractions plus a total molar flow rate, and n dot or n, or whichever way we do it. There's going to be some total molar flow rate, as well as the 5 mole fractions. Those mole fractions are the mole fraction of carbon monoxide, carbon monoxide, carbon dioxide, methane, hydrogen, and water vapor. So we had 6 unknowns. And then the 6 equations that we have the 2 K is equal to Q reactions, equations. Right? K sub m is equal to Q sub m, and K sub water gas shift is equal to Q sub water gas shift. So that's 2. We also have 3 elemental balance equations, meaning the amount of hydrogen entering the gasifier has got to be equal to the amount of hydrogen leaving the gasifier. The amount of oxygen entering the gasifier has got to be equal to the amount of oxygen entering has got to be equal to the amount of oxygen leaving. Here I mean elemental oxygen. And the amount of elemental carbon entering has got to be equal to the amount of elemental carbon exiting. So what I have in equations 3, 4, and 5 are just elemental balance equations. Okay. And on the right-hand side of equations 3, 4, and 5 are the flow rates. Those are inputs into the system. Right? There's going to be a certain amount of carbon flows in, amount of oxygen that flows in, and there's going to be a certain amount of hydrogen, elemental hydrogen that flows in. So that's going to be the right side, and then on the left side, you basically look at how much for the hydrogen one, you look at those species which have hydrogen that are leaving. For the oxygen, you look at the oxygen that's leaving, and for the carbon, you look at how much carbon is leaving in each of those gases. And then, so that's 5 equations, and then of course the 6th equation here is that the sum of the mole fractions has got to be equal to 1. So I just want to point out, when you do it this way, you have 6 equations, 6 unknowns, and this means that this is a solvable problem, and provided that your input of carbon, oxygen, and water vapor was such that it fell in that window of gasification, meaning you didn't supply too much oxygen or not enough oxygen for a given amount of carbon and water vapor. So those are the constraints and input and constraints and outputs. What I want to point out is that there are five inputs. 5 things are going to be able to change the outputs, and that's the carbon, the amount of carbon you put into the gasifier, the amount of water vapor, the amount of oxygen, as well as the pressure of the gasifier and the temperature of the gasifier. So these are the 5 inputs, and then you have 6 constraints and 6 unknowns. So here's some. Here are 2 graphs. The first one, we're going to keep the temperature of the gasifier at 1000 Kelvin. This is close to a temperature of about 700 degrees Celsius. And we're going to vary the pressure. And when the thing to point out here is at constant temperature, as you vary the pressure, what's going to be happening is that, as one would expect from the Le Chatelier's principle, you're going to be increasing methane and carbon dioxide at the expense of hydrogen and carbon monoxide. And what's interesting here is there's very little change in the water vapor concentration. It stays around 20% as you go between 1 and 100 atmospheres. What changes greatly is the amount of methane. You can see if you ran a 1 atmosphere gasifier, you would have virtually no methane in the output. Whereas you could have up to 20 or even get close to 30% methane as you start going up to 100 atmospheres. And So if you did have a 100 atmosphere gasifier at 1,000 degrees Celsius, you're getting close to the point in which the output gas is almost all methane, water vapor, and carbon dioxide. I do want to point out that the two graphs you're seeing here are under the case in which the steam to carbon ratio to the gasifier is 1.0, and the O2 plus 1/2 of an oxygen. So basically, this oxygen to carbon ratio is equal to 0.75. And so under this case, that is part of the reason why we're seeing a lot of carbon dioxide here. Is there's actually a fair, in this example, there's a fair amount of oxygen being supplied into this gasifier in the form of both oxygen and the oxygen and water vapor. Okay, so the next thing I want to point out here is that on the right graph, we're going to keep the pressure at 1 atmosphere, but we're going to vary the temperature. And here in this case, you can see that as you increase the temperature, you quickly destroy the methane, right? And notice that these two graphs are exactly the same at 1,000 K and 1 atmosphere. And that's the case. There's no methane when you're at that case. And so carbon dioxide is going to and methane will decrease with temperature, whereas hydrogen will increase, carbon monoxide will increase, and hydrogen, though, when you get to really, really high temperatures, it may decrease because of the reverse water-gas shift reaction. Some of the hydrogen will go back to water vapor. Okay, the last thing I want to point out on this slide, as I mentioned towards the beginning of this talk, I just want to give you a feel for the relative rates of reaction. So we were talking about equilibrium so far, but I want to give you a little bit of feel for kinetics. And this is going to be the last slide of this talk. Part of the reason why you send the oxygen into the gasifier is because the rate at which oxygen can attack carbon is about 5 orders of magnitude greater than the rate at which water vapor or carbon dioxide can attack carbon. And those rates are 3 orders of magnitude higher than the rate at which hydrogen can attack carbon. So when we were talking about that counterflow moving bed gasifier, so to give you a feel for what's going on there, so the first thing that happens is you put the coal on the top, water vapor will vaporize, so any water that was just sitting around in the coal will evaporate. And then as the coal starts heating up a little bit more, then what happens is it starts pyrolyzing, and those pyrolysis reactions are actually fairly quick. They're not constrained in the way that some of these carbon reactions that I'm showing here are constrained. So after that, any water vapor that has been fed into the gasifier, so after pyrolysis, then you have the steam-coal reactions going on, in which carbon is being attacked by steam as well as carbon dioxide. And these aren't particularly fast, but what's happening is that they're going after any bonds that they can break. And then finally what's happening is as the coal gets down to the bottom, that's where it sees the oxygen. And that's really where the oxygen is needed, because that oxygen is going after graphite, which it would be very, very difficult for water vapor or carbon dioxide to destroy all the graphite bonds. So that's part of the reason why that moving bed gasifier is so efficient is that the oxygen is not needed to help. Oxygen is not needed to help pyrolysis. So there's no oxygen at the top of the gasifier. The oxygen is being consumed only where it's needed the most, and that is to break any carbon or coke that forms. So it's a very efficient use of the oxygen in that type of gasifier. because you can imagine what's happening here is the oxygen is just combusting the carbon, and then that makes CO2, and guess what? Well, that CO2 is now free to attack coal also in a form that's a little bit more efficient, because then it's that Boudreau reaction that makes 2 carbon monoxides. So I just want to leave you with this to give you a feel for part of the reaction, relative reaction rates of coal with various gases at 800 degrees C.